Okay, friends, good morning. We are going to just say a bit about nitriles, which are part of chapter 15. They don't really fit there. They're sort of crammed in there because of a revision of the text. There are 4 reactions involving nitriles. They're not the most important reactions, but at a future chapter, we're going to learn to make a special kind of nitrile, and then your text is going to expect you to do synthesis problems remembering these reactions. So I'm just going to introduce them briefly here. We will not say anything about mechanism. If you want to know mechanism for some of them, you can come talk to me and I'll talk you through it. For example, the one that I already mentioned is that you can use water either under acidic or basic conditions to hydrolyze a nitrile to either the carboxylic acid or the carboxylate. And the important thing to realize here is the carbon of the nitrile is the carbonyl carbon of the carboxylic acid. So this reaction basically replaces the 3 carbon nitrogen bonds in the nitrile with carbon oxygen bonds. Where do those oxygens come from? Water. So this is basically a hydrolysis reaction. If you want to know the mechanism, it's not that difficult to go through, but we won't talk about it in any detail. A second reaction with nitriles is reduction reactions. So you can use lithium aluminum hydride to reduce nitriles, interestingly, to the amine. So here is the carbon of the nitrile, and here is the nitrogen of the nitrile, and you've basically delivered 2 hydrides, and those hydrides come from lithium aluminum hydride. Basically, you need 2 equivalents. Again, the mechanism is not that difficult. We could talk about it, but we won't because we don't have time for it, and it's not that interesting. Another reduction reaction you can do with nitriles is to use dibol. As with esters, if you use dibol, you can deliver 1 hydride to the molecule. You end up forming an imine, which gets hydrolyzed to the aldehyde. This is a big jump and may be confusing to some of you. We won't spend a ton of time on it. The carbonyl carbon from the carbon from the nitrile ends up being the aldehyde carbon. Basically what's happening here is you get reduction of the nitrile to the imine, then you get imine hydrolysis from the imine to the aldehyde, okay? So you might see in the future synthesis reactions in later chapters that are gonna require you to use some of these steps. We won't use them a ton, but I want you to be aware of them so you can do those problems later on without a whole lot of heartache. By the way, the hydrogen from the aldehyde comes from dibol. The last one that's introduced in your text is if you use an organolithium reagent or a Grignard reagent with a nitrile, that will make a new carbon-carbon bond. Essentially, the carbon of the nitrile is like a carbonyl carbon. So the R group is the nucleophile that gets delivered. In blue is the carbonyl carbon. Let's see, I need a highlighter. In purple is the nucleophile that got delivered. Basically, you get addition of the nitrile to form a new carbon-carbon bond and make an imine, and then you have, after that, imine hydrolysis to the ketone. So some of you are going to be uncomfortable with not knowing the mechanism of these reactions. If you want to work through it, I'm happy to do that. It's simply not worth our time, and I'm not right now in class, and I'm not going to ask any questions about mechanisms of these 4 reactions. But I do want you to know them and be able to use them in a synthesis or in a predict the products question like you might encounter in future chapters. Yes?
If you added a second step for the lithium hydride, could you hydrolyze the amine in that one as well?
For lithium aluminum hydride, why do you go all the way to the amine instead of hydrolyzing the imine? In other words, what's the difference between this and dibol? That's not explained in your text, and I don't actually know. So it's a great question, but I don't know. What else? Okay, well, that is the end of chapter 15. Now, the theme of chapter 16 is a reaction that you already know, and that is nucleophilic acyl substitution. We've seen this reaction before when we used a carbonyl compound that had something on it that could be a good leaving group. For example, what about the acid chloride, right? Where Cl- is a decent leaving group. You've seen reactions where nucleophiles attack the carbonyl carbon to get a tetrahedral intermediate. Then you have a negatively charged oxygen in that tetrahedral intermediate that acts as the kicker-offer, and your question is simply, do I have a good leaving group relative to that negatively charged oxygen? In the case here, you sure do, and you get a substitution product where you have a nucleophile. Now, in chapter 13, we were using nucleophiles that were so strong that we had to worry about, after we did the nucleophilic acyl substitution reaction, is a second nucleophile going to come in and we're going to get an addition product. In chapter 16, the theme is using nucleophiles that will basically add once. So there are a bunch of reactions. This chapter is sort of mix and match your carbonyl compound and your nucleophile. We will not spend time going through each and every possible iteration of a nucleophilic substitution reaction. For example, I expect you, if given this situation, to be able to predict and draw the mechanism very easily for conversion of acid chloride to ester. That should be almost, at this point, second nature. That should make total sense. If I changed the electrophile to, instead of an acid chloride, an anhydride, I would still expect you to be able to come up with that ester as the predicted product. And if we swapped out the nucleophile from being OR minus to being, say, an amine, I would expect you to predict very easily that you can make an amide. Or if we instead swapped out the OR minus group for water or hydroxide, I would expect you to predict very easily that you would make a carboxylic acid. All of that's pretty straightforward. All of that you should have and be able to be pretty well good enough on your own. So we won't spend time on it, much more time on it in class. Though, I'll pause and I'm happy to answer any questions you have. Yes?
So, taking like the acid chloride, for instance, reacting it with water produces the carboxylic acid, you said?
Uh-huh. Yeah, water or hydroxide. Yep. Similarly, you could make, if you swap out the nucleophile to a thiol, you could make a thioester. All of that, and that will all follow the same basic mechanism with a tetrahedral intermediate. All right? Okay, the place where it gets tricky is really, the place where it gets tricky in chapter 16 is where we want to deal with either nucleophiles that aren't strong enough to attack directly, or we want to start dealing with reactions involving the carboxylic acid as the electrophile. So we're going to spend some amount of, a decently large amount of time on this, because this is where it gets a little tricky. We've not dealt with carboxylic acids as electrophiles before, and the reason for that is that the most reactive part of the molecule is actually not the carbon-oxygen pi star, but it's the acidic proton on the carboxylic acid. In other words, if you have a nucleophile, and a lot of things that are good nucleophiles are also good bases, the first thing that happens with the carboxylic acid is you deprotonate the carboxylic acid to make the negatively charged carboxylate, And as I told you at the beginning of class, the negatively charged carboxylate is generally very stable, and it is definitely not an electrophile. So this is the universal problem you have with carboxylic acids, is that acidic proton. If you want to do nucleophilic acyl substitution with carboxylic acids, you got to have a workaround, and that workaround usually involves converting the OH into a good leaving group. So we're going to present some strategies for doing that. The first is the simplest, and that is acid catalysis. So this acid catalysis method sidesteps the problem of the nucleophile deprotonating the carboxylic acid, because you're using acidic conditions, so you don't really have a strong base nucleophile present anyway. And the classic example of acid catalysis in carboxylic acid chemistry is the so-called Fischer esterification. Let's see, anybody taken 353 this semester? You already done this one? Okay, so boring, right? But you'll now hear the mechanism. So the idea is that you can take a carboxylic acid and an alcohol, and then under acidic conditions, again, acid catalyst, you can make an ester, and you get water as a leaving group. In this reaction, the ester is your nucleophile, and the thing that leaves is water. So this is a nucleophilic acyl substitution reaction. All right, so let's talk the mechanism. In terms of what's going on here, this is going to be very similar to acetal formation. In fact, the players are almost identical. Do you remember in acetal formation, you had either an aldehyde or a ketone, and then an alcohol as a nucleophile, you used an acid catalyst. In this, we're going to do basically the same thing here. The only difference is your carbonyl compound has an OH group on it. So the first step in Fischer esterification is, because the alcohol is not a great nucleophile, that we're going to protonate the carbonyl oxygen with the acid. That's going to generate this oxonium ion. And now this oxonium ion is electrophilic enough to be attacked by a neutral alcohol. So lone pairs on the alcohol attack the carbonyl carbon, attack the pi star, breaking the pi bond. That gets you to this intermediate, tetrahedral intermediate, that has two OH groups on it, and then this ROH plus group. Now, at this stage, I'm using reversible arrows to indicate that the reaction can go backwards, because this is, like acetal formation, an equilibrium reaction. And as you can see, we're going to push it forward, presumably by removing water to drive the equilibrium forward. If at this stage lone pair electrons on this oxygen kicked down, they could kick off the alcohol leaving group, no problem, right? But if instead we regenerate our acid catalyst by having the conjugate base of our acid remove the proton, then we've got this intermediate. And if you're comparing what we've done here to what we've been doing earlier with acetal formation, you should see that this intermediate looks sort of like a hemiacetal. There's the OH group, there's the OR group. The only difference is there's a second OH group. We don't call that a hemiacetal, but that's sort of where we are. Now, if you're looking at where we need to go, we want water to be a leaving group, and we want the OR group to stay. I don't know where the little apostrophe came from. We'll just erase that. So I've regenerated my acid catalyst, and the idea is, what if that acid catalyst protonates one of the OH groups, thereby turning it into a good leaving group? Those two OH groups at this stage are identical. It doesn't matter which one gets protonated. Okay, if we protonate the yellow OH group, it turns into something that can leave as neutral water. And now this neutral OH group is a good enough kicker-offer to kick off the leaving group. So electrons will kick down and water leaves. That will give us a second oxonium ion that looks like this. And then, of course, water was the leaving group. And as I said, we're going to remove the water to prevent the reaction from going backwards. What would that backwards reaction look like? Well, water is a good enough nucleophile to attack this second oxonium ion. So to go backwards, all you would have to do is have lone pairs on water attack the carbonyl carbon to give you this intermediate. Then finally, in the last step, we will regenerate our acid catalyst by having the conjugate base of our acid remove the proton, and that will get us to the ester. Okay, so that's Fischer esterification. It's an equilibrium process, almost exactly analogous to acetal formation, only we're using the carboxylic acid instead of an aldehyde or ketone, and and like acetal formation, we're removing water to drive the reaction forward. Okay, questions about that? When you did this in 353, how did you remove the water? Silica gel beads? Okay, did you actually put it in the reaction vessel? Okay, cool, that works. A lot of different ways you can do that, but that's a simple one on a small scale. And then, did the ester smell pretty? Did you make a nice smelling ester, or was it? Okay. Esters happen to smell kind of fruity. Well, a lot of them do anyway, so depending on the one you may have made something that smelled like banana or strawberry. Yeah, okay. Great. Questions about this reaction? Okay, so do you remember when we did acetal formation, I said you already have the tools to do acetal hydrolysis. The intermediates are all the same. In a similar way, you can do ester hydrolysis under basically the exact same conditions, only you supply an excess of water. So in the presence of an acid catalyst, and I'm going to just write, when we do ester hydrolysis, I'm just going to write H3O+. So it's obvious that we're using an aqueous acid. That will take you back to the carboxylic acid and release the alcohol. The mechanism for that you should practice as a way to test how well you understand what we've drawn above. But as a hint, the intermediates are going to be all the same. You're just going to push the arrows backwards. So start here and then ask the question, what would I have to do to this product to go back to this oxonium ion? You would notice the oxonium ion has a proton on the carbonyl carbon. Therefore, it would make sense that you have to protonate the carbonyl oxygen with the acid. Okay, follow that through. That's important to be able to do. All right, other questions? Yeah.
So can you just say what you said again before about how it's similar to the acetal formation, the esterification?
Right, the Fischer esterification is similar to acetal formation because the nucleophile is an alcohol, and you have to protonate the carbonyl oxygen first before the nucleophile attacks. And we're using the acid catalyst to trade around who's the good leaving group. Okay. While we're on the subject of what to do with carboxylic acids, I'll give you a second approach. The Fischer esterification is one of them. Use an acid catalyst. Second approach is, but all of these are related to turning the OH into a good leaving group. Second approach is to use something called SOCl2 to make the acid chloride. Now that's a review reagent, right? All of you are sighing in anger and frustration that you learned about that reagent in 351 and you forgot it. Here it is again. And the reaction that we'll introduce is you can use SOCl2 to convert the carboxylic acid into the acid chloride. And we won't worry too much about the mechanism of this reaction. If you want to know what it is, usually you need a small amount of base to make the reaction go. That small amount of base deprotonates the carboxylic acid to generate the carboxylate. So this reaction actually takes advantage of the thing we were worried about to begin with, which is if we use a nucleophile or a base, then the OH is going to get deprotonated, we'll have a carboxylate. In the case of the SOCl2 reaction, that is exactly what we want to have happen, because now we'll use the nucleophile, now we'll use the carboxylate as a nucleophile. Basically what happens is the negatively charged oxygen kicks off a chloro leaving group on the sulfur to generate this intermediate. It doesn't obviously or immediately appear that what I'm highlighting in yellow is a good leaving group, but it is, because it's actually spring-loaded with something that's going to bubble off irreversibly as a gas, and Cl-, which is a good leaving group. So what happens after we use the carboxylate as a nucleophile, Cl- comes in and attacks the carbonyl carbon to get a tetrahedral intermediate. Again, that step is just classic nucleophilic acyl substitution. Then what happens? The negatively charged oxygen in the tetrahedral intermediate is going to kick off not Cl-, but instead it's going to kick off this group, electrons from the carbon-oxygen sigma bond kick down to form a new oxygen-sulfur pi bond at the same time as the chloro leaves. So you have this multi-step or multi-things going on at once reaction that generates the acid chloride, also makes SO2, which is a gas that bubbles off your reaction mixture irreversibly, and then Cl-, which is an excellent leaving group. So you've never, I don't think, seen a leaving group fragment like this before, but this is one of the effective ways to do leaving groups if you can have something break apart into pieces that are either remove themselves from the equilibrium or are very stable on their own. So we'll call that a fragmenting leaving group. That's a mechanism that I don't anticipate, testing you on. So if you want to just memorize this reaction, that's fine. But for me, it's helpful to know the mechanism so I can remember what the reagent does and how that works. Notice that when you do this, you upgrade the carboxylic acid from something that had an OH group, which was problematic in terms of the acidic proton, to something that now is a good leaving group, but lacks the acidic proton. And so now you can use this in all of the easy ways that we talked about previously for dealing with carboxylic, for all of the easy ways of nucleophilic acyl substitution once you got the acid chloride. Okay? This is an easy way to sidestep the problem with carboxylic acids. Okay, questions about that? Yeah?
Why would we elect to do esterification over using sulfate?
Why would we choose to do Fischer esterification versus using Sockel? Because you could make an ester this way, right? You're saying that I make the acid chloride, then I add the alcohol. Fewer steps. With the esterification, you can do it in one step. Second, acid chlorides themselves are sometimes not very stable as intermediates, and so they wouldn't last a long time, and maybe purification of them could be difficult. So it wouldn't be wrong to propose a synthesis where you make an ester using the acid chloride. As I told you before, organic chemists like to have a lot of options, and if you were doing a synthesis, you'd probably try a couple of things and choose which one worked best. All right, others? Okay, let's do the last one. As I said, there are problems with the acid chloride. One is that sometimes the acid chloride is not that stable. Acid chlorides tend to be moisture sensitive, meaning water in the air can react with the acid chloride to go back to the carboxylic acid, which would be really annoying. You spend this time to make your acid chloride, then you put it in the fridge, and then you come back and half of it's gone back to the carboxylic acid. So we like to have another method as well. And the method I'm going to introduce does turn the OH into a good leaving group, but the good leaving group is not the acid chloride. It's something that isn't as moisture sensitive. And the strategy here is using what I'm going to call a coupling reagent. I'm going to call it a coupling reagent because we're going to use this reaction later on in the class when we want to start making polymers of amino acids. And the idea here is this coupling reagent is going to couple or link a carboxylic acid with an amine. So just to illustrate again the problem, imagine that you wanted to use a carboxylic acid and you wanted, instead of making an ester, you wanted to make an amide. So your goal is to do this nucleophilic acyl substitution reaction, right? Imagine that you tried to do it directly. Well, the amine is a base, and the base is simply going to deprotonate the acid. And after the base deprotonates the acid, what have you got? You've got a carboxylate and you've got an ammonium. This is now a salt. Not A-S-S-A-U-L-T, but a space, S-A-L-T. And your text says that if you're really lucky and you add heat, the ammonium salt of the carboxylic acid can form the amide spontaneously. I think that reaction works only in one case. Like, nobody does it that way. So that's not really a valuable method for making this functional group, which is called an amide. Okay, so if we can't do it directly, let's try an acid catalyst. What do you see as the problem with using an acid catalyst? And why wasn't that a problem for the alcohol and when we made the ester? I'm trying to say, why don't we just do Fischer esterification, but instead of using ROH, let's just use an amine? What's the problem with that? The amine's more basic than the alcohol, right? So you've got to worry about now the amine reacting with your acid catalyst, and indeed that's what happens. So you can't do the Fischer esterification with the amine because the acid's not going to protonate the carbonyl oxygen. Instead, it's going to protonate the amine. And then you've got that ammonium thing again, and you're sort of dead in the water. So we can't use an acid catalyst. We need a coupling reagent. The coupling reagent is going to convert the OH into a decent leaving group. So let's introduce the reagent. It has an abbreviation which is DCC. Not to be confused with PCC, right? So it's just alphabet soup around here. Usually in this reaction, your text does not include this detail, but I've done, and other people in the department have done a fair number of these reactions before. You almost always include a non-nucleophilic base. That is a base that is not going to compete with the amine for your activated carboxylic acid. Often these are tertiary amines, and we'll talk in a moment about why they're non-nucleophilic, but for right now you can think about them as being sort of sterically hindered, and that's good enough. This is triethylamine, and it is frequently the non-nucleophilic base of choice. I will draw out the DCC reagent. You don't want to know this, and I'm probably not going to ask you to know the name of the reagent, but it's called dicyclohexyl. So you expect there to be 2 cyclohexane rings. Then carbodiimide is the name of the reagent, DCC. You haven't learned what an imide functional group is, and you won't. We're not going to talk about it. Certainly not, you haven't heard of a diimide before, so you're just going to have to accept on faith the way this reagent looks as I draw it for you. It's a carbon in the middle, doubly bonded to 2 nitrogens, and then each of those nitrogens is itself bonded to not a benzene ring, but a cyclohexane ring. There's lone pairs on the nitrogens. So that's a weird functional group that you haven't seen before. So this is where you have to try to use your intuition and relax your eyes a little bit. Nitrogens are more electronegative than carbon. So you predict that this carbon should be pretty electron poor. Also, you see the 2 carbon-nitrogen pi bonds. This is like a carbon that's involved in 2 imines, right? Now, we talked last time about how imines can be electrophiles in the same way that carbonyls are electrophiles. So when I look at the dicyclohexyl carbodiimide, I see something that looks like a carbonyl carbon, only it's involved in 2 at the same time, and the carbon should be especially electron poor. Okay, questions about how you see that or reason through that? If you think about that as being a carbonyl carbon, which I'm going to label as blue, then it becomes a little easier to see what's going to happen in this reaction. All right, so it turns out we're going to use, let's see, we're going to use the carboxylic acid as a nucleophile. What we will do is first use our non-nucleophilic base to remove a proton and make the carboxylate. What I'm showing you here may be different than what is in your text. I think your text doesn't show the presence of the base that you use and instead takes care of the proton transfers in a reasonable way. What your text shows you isn't wrong, so you can learn it either the way I'm drawing it or how the text draws it, and either of those is fine. The negatively charged carboxylate oxygen attacks the carbon of DCC, and we break the pi bond, and electrons move out onto the adjacent nitrogen. That's going to create an intermediate that looks like this. Here's the carbon that we just attacked. I'm going to now abbreviate the cyclohexane rings with the abbreviation CY. I hope that's okay. If it isn't, I don't care enough to change it, so there you go. We now have a negatively charged nitrogen, and it will pick up a proton from the conjugate acid of our non-nucleophilic base. And that will generate, and I'm going to go down a page right there, the following intermediate. Okay. Now, that does not look like a good leaving group. It will be for reasons that I will show you in just a little bit. But importantly, at this stage, you can see that it lacks the acidic proton. Okay? So that's much more complicated a leaving group than you've seen before. But go with it for now. It lacks the acidic proton. So now is the stage at which we introduce the nucleophile. So what some people do when you do this reaction in practice, you don't need to make a note of this on any sheet of paper, but you actually put the carboxylic acid into solution with DCC first to allow this reaction to happen. Only then do you introduce the amine. So let's imagine what would happen if we introduced the amine as a nucleophile at this stage. The amine's relatively nucleophilic, so we can do this. The electrons kick up to give you a tetrahedral intermediate. Now, let's draw what we have here. The amine is still positively charged now. The nitrogen that did the attacking is now this group, and it's positively charged. Over here, we have the oxygen. I'm sort of rotating around this carbon-carbon bond to put this doubly bonded nitrogen sort of pointing down in this direction. There's a reason I'm doing that, which I'll show you in just a second. All right, so do you see what we've done so far? We've now had the nitrogen attack. Ultimately, if you look at where we're trying to get, we want to get to the amide. And the nitrogen needs to lose a proton so we can get to the amide. Otherwise, it's a decent leaving group on its own and could get kicked off by the pink kicker off or oxygen. Instead, we want what's in yellow to be kicked off as a leaving group, but if it left, it would be negatively charged. And so there's actually a way we can take care of both problems at once, deprotonating this nitrogen and protonating the leaving group as it leaves. The reason we can do this is because the atom we're going to use to do the deprotonating on the leaving group is 6 atoms away from the hydrogen. If you build a model, atoms that are 6 atoms away from each other or 5 bonds away from each other are actually pretty close in space and they can touch. If it gets much shorter than that, there's a lot of strain in arranging the two groups so that they can touch each other. If it gets a lot longer than that, the groups have to swim around for a while before they can find each other. So because this proton here is 6 atoms away from this nitrogen here, we are set to do something all in one step that we could otherwise do just by deprotonate that and then protonate this and then do the chemistry. So what I'll show you is the all in one step version. Electrons on the kicker off or oxygen kick down and kick off the leaving group. But instead of showing these electrons being on this oxygen as a negative charge, we're going to go ahead and have them move here to form an oxygen-carbon pi bond. That requires us to break the carbon-nitrogen pi bond, and that would result in a negatively charged nitrogen here, which just happens to be perfectly placed to deprotonate the amine. And then in one step, that gives you your amide. And then here is the neutral leaving group now. It's got a carbon-oxygen pi bond. That oxygen came from the carboxylic acid. It's got 2 nitrogens and then 2 alkyl groups, these cyclohexyl groups. This is called dicyclohexylurea, or DCU, and it is very stable. And is easy to separate and isolate from the amide bond that we made. So here is our amide product. And notice that we sidestepped the issue of the acidic proton. And we also, I think that's all I wanted to say about that. So any questions? Okay. All right, so we've seen, go ahead.
So we do need to know this mechanism?
Yes, you can learn it as I've shown it, or you can learn it as it's shown in the book. Okay, what else? Yes?
This is concerted. You didn't just go out in one step to be efficient. Or does that all happen at once?
So by concerted, I assume you're referring to this leaving group leaving,
Yes.
forming the pi bond, and the electrons kick down. To answer that question, you would need to know if anybody has done some kinetic experiments to demonstrate this. This could be a mechanistic hypothesis. There might also be data showing that it's the case. In any case, in kinetic experiments, it's hard to get details about things that happen after the rate determining step. So all of that presupposes that this is the slow step, and I guess I don't know. It's reasonable because of the reasons that we talked about, but one of the reasons that I'm saying you can learn it as it is in the text too is because I don't know what data supports this versus the other way. Okay, yeah.
What kind of questions, since a lot of stuff taking your exams, like what kind of questions can you get about mechanisms?
What kind of questions can you get about mechanisms? So supposing that we had an exam this week, and supposing that I had written a question on the exam about mechanism, what would that question be, right? Well, I'll give you... Yes. Well, okay, so one of the ways I ask questions about mechanism is to say which of the following steps is correct, or which of the following steps is unreasonable. Supposing you were doing a nucleophilic acyl substitution reaction, and I'm just going to keep this general, and I was asking which of the mechanistic steps is reasonable. Well, one of the incorrect ones would certainly be this. Tell me what is wrong with that. Well, I told you it was wrong, so you're naturally suspicious. You have to imagine yourself in the fog of war, 2 hours into a test, tired, ready to go home, and you look at that and suddenly it looks pretty dang reasonable. It looks pretty dang reasonable because you're like, hey, leaving group, I wanted yellow, there we go, relieving group, nucleophile. That looks like an SN2 reaction. Hey, I remember that from 351. That's perfect, right? Wrong, exactly wrong. Because the LUMO of the electrophile is the pi star. So you have to always attack the carbonyl carbon to get a tetrahedral intermediate. So I often put something like that as options, right? Either the wrong one that I showed you or then the correct one here. And you got to know about it to get it right. Yeah, so that's one example. Okay. Let's see. So others. Yeah.
So for the coupling reagent, do you need to know the mechanism in the book and from the lecture?
So for the coupling reagent, do you need to know the one in the book or the one from the lecture? What if I could restate the question in a way that I think is useful to everyone? What you want to know is, will option A on the test be what I showed you, and option B on the test be what the book showed you, and you have to choose between the two? I mean, if you're in that situation, just choose what I do because you want to appeal to my ego, right? Isn't that? No. Basically, I'm not going to put you in that situation, so you don't have to worry about that. Okay. Others? Right. Well, I want to talk about esters again because you can do ester hydrolysis, as I said, by the reverse of the Fischer esterification using aqueous acid. But there is another option for ester hydrolysis that is important historically and gives us a chance to review some things from 351 and from and look ahead to some stuff from biochemistry. This is a reaction that's called saponification, from a word for soap. Okay, so it turns out you can hydrolyze esters using a reaction that our ancestors used to make soap. I'll show you the simple reaction mechanism. Here is a generic ester. The conditions for saponification are strong aqueous base. And what this does is it makes the carboxylate and releases the alcohol. And the mechanism is exactly what you would expect. Hydroxide attacks the carbonyl carbon to give you a tetrahedral intermediate. At that stage, the negatively charged oxygen could presumably just as easily kick off the OH minus nucleophile as to kick off the OR minus leaving group, right? They both have equal leaving group ability. So that first step you would predict is reversible. However, once the kicker-offer oxygen kicks off the alkoxide leaving group, that changes the situation forever, because what you just did was remove a leaving group that is a strong base, and you just made a carboxylic acid. So in that moment, lone pairs from the alcohol, let's see, I don't like that arrow, I needed just a little bit more space. Lone pairs from the alcohol remove a proton from the carboxylic acid. That step is irreversible. Do you want to know how you can tell it's irreversible? Just look at the pKa of that proton, which is 4, versus the pKa of that proton, which is 16. The strongest acid loses its proton, and there you stay. You've fallen into the thermodynamic sink of the carboxylate, and the reaction's over. Now, later on, if you want, you can gently acidify the reaction mixture, adjust the pH to higher than 4, and you can isolate the carboxylic acid. That's not hard. But the first product is the carboxylate. What does this have to do with soap? Well, you may not know this or appreciate this at this stage, but fats and oils are esters. Fats and oils are a type of biomolecule which we call triglycerides. You've ever gone to the doctor for your annual checkup and they take a blood test, they're analyzing your triglycerides, they're looking for what I'm about to draw. Triglycerides actually involve a 3-carbon alcohol with an OH on each carbon, and then each OH is tied up as an ester with a long chain carboxylic acid. We call that a fatty acid, and they usually have even numbers of carbons. So 2, 4, 6, 8, 10, 12, 14, 16, and we'll just put R's there, okay? That's a triglyceride. Now, imagine what happens if we were to do the saponification reaction on a triglyceride. In the case of our ancestors, the triglyceride was usually animal fat from whatever animal that had recently been slaughtered. And the strong aqueous basic conditions was usually potassium hydroxide, which they got from ashes. So what are the products going to be if I do the saponification reaction on this triglyceride? What should I have on the alcohol side? Okay, I'm detecting some consternation or some reluctance to commit. Either of those is okay. Does it make it simpler if we do this? So what are the products of saponification for an ester like that? It's the carboxylate and then the alcohol. So now apply that to the triglyceride. What's the alcohol? The 3 OHs are all on the same carbon. I'm sorry, all on the same molecule, 3 different carbons. And then I'm going to have 3 of these carboxylic acids. This one is called glycerol, the 3-carbon alcohol, And then these carboxylic acids, as I said, are called fatty acids. Okay, what we'll do next time is we'll just talk a little bit, review something from 351 about the properties of these fatty acids and why they work as soap. Yeah? Yeah, would you need 3 equivalents of potassium hydroxide to make this work? Yeah, they probably used excess.